So we've been working really hard this year, and kind of halfway last year, in trying to work out the whole AI environment, what the real impact is for storage and how we can really help, taking our existing technologies, our existing services, our existing understanding of the HPC networking client environment and see how we can make that work genuinely for the whole AI environment. Across the scale, so we already have quite a lot of customers, and even before we started thinking about this, there were customers running AI workloads at very decent scale on DDN platforms. Probably we're one of the most AI-centric data platforms even before we started this work over 1 year ago, because our customers are pretty adventurous and they've already been experimenting with GPUs and advanced CPUs and putting these AI frameworks on them. So what we're really doing here is we're taking these data at scale services. So at DDN, we have 200 plus engineers who just do data at scale. But that's like a catch-all term because all our customers really, that's their thing in common. So we do object stores, we do burst buffers, we do parallel file systems, we do analytics, but we always do it with scale in mind and performance in mind. So we're taking those services people and challenging them to take the platforms and integrate them deeply into all these workflows. And I'm going to take you through the story of what we've done there and what the products are that come out of that. So here's my kind of view of where we are in this AI space. There's obviously still, so even now, a lot of experimentation in AI, and we have regular customer meetings where they're generally just starting. So they've just bought a reasonably small implementation of usually GPUs, and they've started experimenting with AI frameworks, and they've got a little bit of data, and they're just working things out. They're just crafting some frameworks. They're learning the whole data science problem themselves. You're often starting from scratch. And it's a huge investment for these customers. So even the GPU side the capital cost can be fairly large, even for a small system. But then they've got to acquire the data somehow, and that can be an expensive or very effortful process. And then the data scientists need to be highly knowledgeable. It's a very different area from traditional HPC, so the data scientists need a lot of investment in developing their own personal knowledge. So we see this AI community is definitely less knowledgeable than the HPC one. And HPC, at this conference and in this room, you see people who know the very minute details of networking and protocols and all this kind of stuff. In the AI, not so much. So the data scientists who are working on this data are really kind of genuinely high-level people. So one of the messages is we need to make things a bit simpler for them across the board. The AI frameworks as well don't make life easy because they're also developing very rapidly. Obviously, that's a good thing, but also it makes life difficult for people who are working in this area because the frameworks are emerging, developing new ways of manipulating the I/O in order to make them more efficient, becoming more parallel as time goes forward. So the whole area is, it's fraught with people who are just learning the area. The frameworks themselves are moving on. And, of course, the whole domain is expanding, including the data itself. So we've been working on these platforms which are heavily qualified, heavily tested, and really can cope with this environment. This environment is not just one that's technical. It's also about people. It's also about whole solutions and integrating into those environments properly. So A3I, Accelerated Any Scale AI Solutions from DDN, is the name we've put to these set of solutions, set of reference architectures that take our products and fit them into the AI workloads. And one of the things we can say about DDN is we can do scale-out performance flash and disk. So capacity and performance in one solution, in one file system, in one namespace. And how many people in this audience have got or who have worked with a DDN system which combines both SSDs and hard drives? That's like about all the customers, I think. So we're kind of unique here because many of the newcomers, they're all flash. And we're not just flash. We've been working with hard drives as well, and that's really important in this area. So one solution, fully integrated and fully optimized. And we're definitely trying to look at the whole workflow. So you'll see out there's lots of press releases and stuff really about just feeding GPUs. Just that little small element of the workflow is getting large amounts of data into a GPU and an AI framework. It's an important problem, but it's not the only one. And really this whole workflow is the more important thing longer term. And it's a bit like HPC. If you think back maybe 10 years, then HPC customers were often saying, give us as many chips as you can, many processors. We want cores, we want clock speed. And really that pattern's changed over time. So now there's much more focus on how we manage the data at scale for supercomputing and high-performance computing workloads. We think the same is happening with the AI. So the first frenzy is really about, oh, how many GPUs can I have? How many cores can I have? And then it gets a more mature conversation. We think about how can we manage this whole long-term AI data lifecycle. So here's where we've come to. This is kind of a picture which really summarizes what we think are the important aspects of a real AI framework that's going to work with the entire data lifecycle. So it is important, right up here, to meet the demand of the GPUs. So it's not the be-all and end-all, but certainly it would be great if we could deliver saturation-level performance into those scale-out GPU systems, into those AI frameworks. But these other areas are equally important. So firstly, flexible access. So what do I mean by that? Well, maybe people have HDFS data lakes, or maybe they're doing unusual ingest operations. So maybe they've got highly bursty ingest, or maybe they've got many, many concurrent threads coming from all sources across the globe coming into this system in order to feed the data lake that's going to then help the neural network get trained better. And then these other two aspects, scaling speed and scaling capacity, this kind of relates to the fact that the user community is pretty young, and they often start small, and who knows where they're going to grow to. So some of our customers are really the largest systems in the world in terms of storage, and some of our customers are really the smallest. And mapping the space flexibly between the starting point and the potential endpoint, and allowing people to do that, make that path with a flexible, with either flexible performance or flexible capacity, and doing so economically is important. So not constricting them to a specific domain is just as important as all these other areas. So we've always done scaling well and independent scaling of performance and capacity. You'll see these new systems coming out, and I'll show you some more slides later on. There's an AI200 and an AI400, and I'll talk about those later on. But in brief, the AI200 and 400 are flash-oriented performance IOPS machines, entirely integrated and ready to go. So whole AI platforms based on flash, ready to go into your environment. If you want more flexibility in terms of being able to scale the capacity, then the AI7990 allows you to combine flash with disk and manage those pools and scale those pools independently and scale whichever way you want. So 3 kind of use cases to show you how these kind of systems are being implemented in practice. So this shows, I think, probably Sanger have some new microscopes as well as Pete. You probably have microscopes as well as the genome problems today, and many of our customers have the same kind of issues. So the image problem is becoming very large, and I think most people know that inference, looking at very extremely large images and working out if there's any tumorous components into those cells is a hugely growing sector of this life science market today. In autonomous driving, the shape of the problem is rather different. It's not really this sort of fast flash inference problem. It's about massive scale globally. So one of our largest customers is an autonomous driving customer. And they have hundreds of cars, maybe thousands of cars, which are collecting data from the streets. And of course, every day they come and park up, and that data needs to be ingested, a very bursty ingest, a very large amount of data from a vehicle into this AI framework. So they need to cope, number one, with this bursty ingest. So part of that workflow is moving data from cars into the systems. Let's make sure that isn't a bottleneck in their workflow. But majorly it's about scale, and it's about volume. So this is not something you could do with an all-flash system because the scale is too large, the volumes are too large. We're talking about many, many hundreds and hundreds of petabytes. And being able to flexibly combine flash with hard drives is critical for these large-scale autonomous driving workflows. Here's a customer, Standard Cognition, very exciting. They're using IME, Infinite Memory Engine, and they use this other characteristic we have, which is transparently creating a flash cache in front of a namespace, but not doing so at extremely large scale. In fact, doing so at very small, manageable scale, and their simplicity, ease of use is critical. Because what they do is they take these small systems and they use these systems in combination with an AI framework, an inference engine, to identify what shoppers are putting into their baskets and taking home with them. So they can automatically charge them for what they've purchased without the whole checkout stuff going on. So automated checkout is a very interesting area, very interesting application of AI. And what it's really asking for is fast flash for inference, scalable storage, but in a small, neat, simple package. So the AI200 is a 20 gigabytes second. It's around, well, we call it around 1 million IOPS, but actually we saw 1.6 million IOPS just the other day on my system in 2U. With the AI200, we've taken Exascaler and we've compressed it into the system and made it much more simple to deploy and much more manageable to implement and integrate into these AI workflows. So it's a 2U system, over 1 million IOPS at block and getting on for 500,000 at file level. And we deploy it in 3 configurations to keep it super simple. None of these huge plethora of options, small, medium, large, then scale out to where you want to go. But that's not all. The i400 is a 40 gigabyte a second system. So this is really twice what you'll see anything out on the market. So you go and find the best, fastest thing on the market. This is twice that. It's a 40 gigabyte a second in 2U, all flash, scale out appliance. Again, start really small. Start with 2U, with a complete solution. Everything's in there. It's ready to go with a file system and all the services you need in just 2U and up to around 150 terabytes. And of course, that number will go up as capacities increase. So as I say, small, medium, large. You can start with 1 unit, 2 rack units. And if you want, you can then scale that up to having 2 of those, 4 of those, 8 of those. And as you know, parallel file systems are inherently linearly scalable. We take advantage of that to give you a complete flexibility in how you grow a flash platform. For even more flexibility, though, you want to add drives, because you might have this, let's say, a relatively modest hot flash area from which you're doing AI training, but you might have a very gradually but continuously growing data library. And that's not always hot, so you want an economic way of managing that very large capacity. The AI7990 has the same features we saw before. It's entirely packaged. Everything's in there. It starts at 4 rack units. You can scale it out. But in this case, you can scale it out with either flash or hard drives or a bit of both. So what about this sort of workload? What does it look like? Here we've got a picture where we're showing a deep learning platform, an AI platform at the top. And we've kind of roughly looking at the characteristics of a generic AI environment, a deep learning environment. So the first thing is, as I said before, the idea of having a pool of flash and a pool of drives and having very fast data movements between them and as transparent as possible a tiering mechanism between them is really important for these workloads. It's bursty and all streaming ingest is a characteristic of our customers, and these data scientists can access and move data in and out of this platform through a variety of protocols, NFS, Samba from HDFS, whatever. Up here, though, is these characteristics of the workload. And, you know, AI really is the opposite of HPC. HPC, we see these very write-intensive workloads. It's not always the case, but at least we kind of hope to think that they've got quite a lot of sequential data in them, which is, you know, sometimes the case, sometimes not. Now, look at AI. It's almost entirely read, and it's almost entirely random read. And it's quite a lot of the time small random read. So we've gone from this HPC workload, write, sequential, to AI, random, and read. So this case here, we look at a customer of ours actually uses 18 kilobyte memory mapped random reads into very large files to push their TensorFlow application. So it's a very characteristic workflow. So these systems need to be able to cope not with that sequential write pattern, but with that random read pattern with those protocols that are being used in those areas. And why is a parallel file approach a good way to go in order to tackle this stuff? And remember what I said before, people are often starting with 1 GPU, 2 GPUs, a little workstation that's getting to 8, and then they're going to multiple GPUs. Their data is growing very fast. And we're seeing in the markets, the competition tends to be using NFS. And Case mentioned this before. So Case said, well, it's all very well having, or maybe I'll paraphrase you, it's all very well having lots of flash, and the applications are there, but what's happening in the middle? What's happening between those things? And this diagram really talks about what happens in the middle. And we're contrasting ourselves against NFS. So with NFS, we see some competitors, and they've got some really amazing, genuinely amazing flash systems, nice flash file systems, beautiful approach to managing flash. But where they're really constrained is how to deliver the potential inside that flash device through to the AI workflow, because they're limited by an NFS protocol. There's no genuine intelligence, there's no RDMA, there's no parallelization in that I/O path. With a parallel file system, of course, what we all know is that at a very granular level, each application, each container, each GPU system can spray the data fine-grained across all this parallel file system. And it can do it with RDMA, and it can do it with InfiniBand or 100 gigabit Ethernet using the fastest networks out there. And we can do with it to a limitlessly scalable namespace. So all these are things which are characteristic of a parallel file system, like the AI200, the AI400, and the AI7990, which certainly aren't characteristic of anything, however fantastic it might be, when it's using NFS. We've gone a little bit further than that, though. So inside many of these GPU platforms, there's a containerized approach. Who's played with some of these containers in this room? Probably about 5 or 6. So these containers work a little bit differently from standard HPC, right? And it means you can do some cool tricks. And what we can do in particular is we can use the containerization approach to make sure the I/O path between the application, the AI framework, and the storage is absolutely perfect. We can squeeze everything we can by taking advantage of this containerized approach. In particular, we can pin the activity of the AI framework through an interface so it can scale across the interfaces into the GPU system. So you'll see what the effect of that is in a couple of slides' time. We've gone an extra step further in working out how to fit an exascaler client right inside the framework and connect right to the application. Here's result 1. Result 1 is over 10 gigabytes a second, over 100,000 IOPS into a single application. Not a single system, into a single application. Point 2 is into a single system. In this case, it's a DGX1. It could be other GPU platforms. HP have got the Apollo 6500. There's a bunch of others out there that are extremely popular. In the DGX1 at GTC, we demonstrated this 38 gigabytes a second throughput, read throughput into this DGX system. So one machine, nearly 40 gigabytes a second. So nobody else is coming anywhere close to this because they're not really using a parallel file system like we are.
Question?
Yes.
Did you have clients for Lustra installed on the DGX1?
Yes.
Because this is not supported by NVIDIA. They say, if you have problems and we see it, please uninstall it, then we support you. So that's why we uninstalled our GPFS client from the DGX1. Yeah,
we're working closely with it. You'll see some news on this over the coming days. Leave it at that. So that was synthetic. Here we go to real workloads. So here's ResNet 152, ResNet 50, Inception version 3. These are the kind of classical real AI frameworks that are being published today. The figures you see here are around double the ones you've seen published so far. So if you look out there on the internet, look at the popular people claiming to be AI ready, they've got about half these numbers here. So where we claim 4,124, they're around 2,000. So this optimization, the implementation of parallel file system has got real benefits into these workloads. There's a bunch more. So red versus gray shows DDN versus an NFS protocol over the same bandwidth network. Now this is it looks the same, but this is slightly different. This is kind of one of our points. So what I just showed you was a bunch of examples of real AI frameworks and some speed-ups into that. But actually the majority of the I/O contention is not in neural network training. The majority of the problem is in those other areas of the lifecycle AI data. In particular, it's in the munging, it's the data transformation, it's what you do, what the data scientists do to prepare data prior to this training operation, or in between the workflows involved in training. So here you see TensorFlow, TF record is a process which basically prepares data for a TensorFlow operation. It takes a pile of image files and it munges them into a big shared binary file prior to a neural network training operation. And here we see around a 2.5 to 3x speed up using a DDN platform on these, non-training oriented workloads, on these munging transformation workloads. So to summarize, we've done a huge amount of work in deeply integrating our parallel file systems into the heart of these AI frameworks. We've done that to eliminate the I/O bottlenecks associated with NFS and take advantage of RDMA fast networks, reducing latencies. We've also got this inherent characteristic of being able to scale SSDs and HDDs and do so independently, but still enable them to be tightly integrated together for a very transparent experience for users. And we can also apply those flexibly into your workflows. I'm skipping back a couple of slides. So, and these are the platforms which we're really announcing. You'll see some announcements tomorrow and today. We've got much simplified solutions, factory configured, delivered to customers, ready to go to deliver the sort of answers you've been seeing in these slides today. Thank you. Any questions? Case, go ahead.
Well, it's again the luster versus GPFS, because there is still a few, so this is all very luster oriented, and I guess your AI approach is very much focused around luster. Still, like us, more of an enterprise-like customer with need of features that aren't available in luster today. So where does that put us in terms of being able to use these new platforms? Are we going to be expecting that new feature set inside luster, or are we going to expect GPFS inside the new platform for mobile?
So the first thing is the AI200, AI400, AI7990, they are exascalar based, they are luster based. We do have some very strong plans to enhance our roadmap to help exascalar get even further into these AI frameworks along the lines of what you're hinting at. So come and talk to us. We're working on heavily on roadmap direction, on thinking how to improve how we fit into the most extreme enterprise environments we can.
Think snapshots, think replication.
Think of all of those things, exactly. Yeah, precisely. And as we saw, we had a bit of a hint before, right? So we already talked to Sims, and Sims talked to us about his exascalar and ZFS. And so he can run snapshots all day, right?
Indeed.
So I'm going to have to brush up my luster knowledge.
Yes, good idea.
I'm wearing the shirt. Choose luster.
Any more questions? Thank you very much.